It's Friday, and it's the 3rd, and we're doing 7-1 trig identities and proving trig identities. So, for example, let's get a nice example here. All right, let me give you a nice easy one to start. Ready? Where is my screen? No, not you. You. There you go. So, consider the following. Cosecant. Give me a pen. It's not giving me a pen. Okay, that's good. Okay, give me a pen. Hello? We only got 29-minute short periods today. What are you doing to me? Hello? Okay, why is this acting stupid? Yeah, now it's writing, but it's not writing on my smartboard. That's in a layer. Wait. Okay, something went screwy here. Sorry, hang on. I have to restart my little smartboard here. Dun da da da. Okay, let's see if this works better. Come on, smartboard. We don't got all day for this today. Come on. Okay. Kindly consider the following. Cosecant of theta times the tangent of theta is secant. Is secant of theta. Yeah, this is acting wacky today. I think my Windows is about to crash or something. I don't know. Now, I'm asking you if that's an identity or not. Now, how do you know? What is an identity? What does that mean? Have you ever encountered this before? This comes up a lot in trig. Not so much in algebra, but a lot in trig. This is an algebraic equation, right? So it could happen in algebra, but what happens here is, usually in an equation like this, you want to solve for the variable. You want to solve for theta, right? What I'm saying is that in an identity, anything works. You can plug in any number for theta you feel like, and it's going to work. So that's my statement. This is an identity. Can you prove that it is or it isn't? All right, so what's an identity? An equation that's always true. It doesn't matter what you plug in for x or theta or whatever. So you don't have to solve it. It's always true. But how do you prove it? Multiplying it. That's a little dot there, right? Okay, so we're doing two things today. What's an identity, and how do you prove that it's an identity? So here's my statement to you. True or false? This is an identity. This is my question. True or false? This is an identity. How can you prove it? Have you ever done identity proofs before? Yeah? Okay. So what do you think? Any ideas what you could do? I'll give you a hint. You know that cosecant means 1 over sine. All right, let's write that. 1 over sine. Okay, my pen is acting really stupid today. Something's wrong with my Windows. I don't think it's a tablet, but whatever. And we also know that tangent can be written in terms of sine also, don't we? Sine over cosine. So when all else fails, let's convert everything to sines and cosines. Now, we're really asking the question. I don't know yet. It's like a check when you're checking your work after solving an equation. So I'm not sure if it's equals yet. I'm asking. What's secant? If cosecant is 1 over sine, secant 1 over cosine. Now, is that true? Yeah, it is, because look, the signs cancel, and you get the same thing on both sides of the equation. So the question is, are they the same? And the answer is, yeah. It's sort of like a check, right? When you solve an equation, you plug your answers back in, and then you check, right? Okay, now this is the game. We're not doing algebra. We're not crossing the equal sign. We're keeping the right-hand side separate from the left-hand side. We're simplifying, canceling stuff out, whatever, rewriting it in such a way that both sides are definitely the same. So does it matter what I plug in for theta? Both sides are going to be the same of whatever I plug in for theta, as long as it's defined, right? Remember, when is cosine 0? Do you know an angle that has a cosine equal to 0? 90 degrees. So 90 degrees doesn't make sense here. It's not part of the domain of the problem, right? This is not defined at 90 degrees. But for angles where it is defined, this is true, so this is true. We proved it. So that's an identity, and that's an identity proof. Okay, good. Let's try another one like that. What do you think about this? Are you ready to go ahead? Anyone stuck? Questions? Comments? No? Yes? Maybe? Good? Okay. Try this one on for size. Can you prove that this is an identity or not? I mean, it may not be. Who knows? Let's see. Tan theta, 1 plus tan theta over 1 plus cotan theta is equal to just plain old tan. Is that true for all theta? Well, the game here is simplify this side so it looks like that side. Now, you could do what we just did, change everything to sines and cosines. But I think we don't have to get that crazy. Because this can all be written in terms of tangent, can't it? That's already in terms of tangent, that's already in terms of tangent. What's cotangent, really? 1 over tan, right? So we write everything in terms of tangent, we might be able to do this. All right, let's do that. 1 plus tan theta over 1 plus 1 over tan. Is that, again, I'm asking the question, is that in fact tan? Okay? Yeah, my colors are all screwed up today. Well, let's see. How do you deal with a complex fraction like this? The idea is to simplify it. And if we simplify it correctly, hopefully we're going to get this, because I can't simplify this anymore in terms of tan, unless I want to write in terms of sine and cosine. But let's say we don't have to do that. Sometimes you don't have to. Sometimes you simplify everything in terms of sine and cosine, or sometimes you simplify everything in terms of secant tangent. That works sometimes. Or cosecant cotangent. That works sometimes too. So I'm going to stick with tan here. How do you simplify this fraction? Well, first, can you add these two numbers? Pretend they're numbers. Pretend they're fractions. How do you add fractions? Forget the top, just the denominator. You need a common denominator. Well, this is really 1 over 1, isn't it? So what's the common denominator? Tan. So multiply this top and bottom by tan. Okay. So let's see. I get 1 plus tan on top. I didn't touch it. Over tan theta divided by tan theta plus 1 divided by tan theta. And again, the question is this the same thing as tangent? Are we trying to prove that this is an identity? It's true for any theta. We've got to do an identity proof, get both sides looking the same without crossing the equal sign. But what's nice about this? How do you add two fractions to the same denominator? Add the numerators, keep the denominator, right? So 1 plus tan theta over tan theta plus 1 over tan is tan. Well, is it looking good? I don't know. What do you think? Is it looking like we're going to get what we want? We want this on both sides. Yeah, because how do you divide by a fraction? Multiply by reciprocal. So the numerator is 1 plus tan theta. The denominator, flip it. We're going to multiply by the reciprocal of the denominator, so flip it. Tan theta over, I don't really have to do this, but can I do this? Is this the same as this? Why? Commutative property of addition, right? It doesn't matter which way you add the order, okay? I'm just making it obvious. What am I saying? They're exactly the same. If this is over 1, right, and you're multiplying, do you get this? Okay, but you got to say so. The last step has to be one side looks exactly like the other side. That's why it's called an identity proof. Both sides have to end up identical. So if we did everything correctly, all our algebra here is all correct. If this is true, this is an equation, then this is an equation. And if this is an equation, this is an equation. And so is this. And so is this. So guess what? We proved this is true no matter what theta we plug in. Because I don't care what theta I plug in, tan of theta has to equal tan of theta. Duh. As long as it's defined for theta, the theta you plug in. Right? So did everyone get that whole proof? Anyone missing anything? Would you be able to do a proof like this on your own? No, really? Let's practice. Practice makes perfect. Boom. Let's try another one. How about this one? Sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine apparently reduces to this. That's a theta. Do you believe it? Wait, hang on. Yeah, that's right. Okay. Well, again, you're adding two fractions, right? So what do you need? Common denominators. All right, so what do you think the common denominator would be? Well, all right, let me put it this way. What can you multiply top and bottom here by and here? 1 plus cosine to get the same denominator, right? These two denominators have no factors in common, so the common denominator is just multiply them together. So multiply top and bottom by sine, so you get sine times stuff. Multiply top and bottom by 1 plus cosine, so you get sine times stuff, the same stuff, right? Okay, so I'm going to set sine squared, I'm multiplying top and bottom by sine, over sine theta times 1 plus cosine, plus, now here I'm multiplying top and bottom by this, so 1 plus cosine theta squared over sine theta times what I multiplied it by, right? There it is. So good, you got a common denominator. Wow, so what? That made it worse. I'm trying to simplify this. It looks worse. Is some way to simplify this? Well, how do you add two fractions of the same denominator? Add the numerators. Okay, so we get sine squared theta plus 1 plus cosine theta squared over sine theta times 1 plus cosine theta. You add the numerators, keep the denominator, right? Well, it's not looking too good yet, is it? I don't know. It's not obvious. Right. What's your favorite F word? Foil. That's what this is, right? Can you foil this out? Let's see. I'm going to leave this alone. Now, do it in your head. This is 1 plus cosine times 1 plus cosine, right? So first terms, 1. Outer terms, wait, should I write it? What? It's cosine, right? Inner terms, there's a 1 times a cosine, so cosine. And last, cosine squared. All right, and the denominator stays the same. Didn't do anything to the denominator. Okay, now all of a sudden my tablet seems to be working okay. I think my Windows was glitchy, trying to crash on me there. That's why I don't usually use Windows, but whatever. Okay, wow, this is really looking a lot more complicated. Well, maybe not, because do you know what sine squared plus cosine squared is? That's a trig identity you should know from kindergarten. Everyone knows this from birth. In the womb, you knew. Sine squared theta plus cosine squared theta, no matter what theta is, sine squared of an angle plus cosine squared of the same angle is always, nobody knows the trig I've seen. 0, no, not 0. No, oh God, we got to do it. Here we go. You ready? Here we do it. Da, 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 da. Remember the unit circle? Okay. Remember in the unit circle we said if the radius is 1, that's what makes it a unit circle. These coordinates are sines and cosines. Remember we talked about this? Okay. So this x value is the cosine of theta, right? What's the cosine of theta? Adjacent over hypotenuse. X over 1 is x. So the cosine of theta is the x value of that point. The sine is y. If the hypotenuse is 1, what's the sine? SOHCAHTOA, opposite over hypotenuse. Sine is y over 1, sine is y, or y is sine. All right. But what does Pythagoras say about these three sides? Remember Pythagoras? A squared, b squared, c squared. This is a. This is b. So cosine squared plus sine squared is always 1. There you go. I knew you knew it. See? Oh, God. And people say you don't know stuff. Okay. Did I leave that too quick? X squared plus y squared is 1 because it's a right triangle. Pythagoras said if you have a right triangle, the sum of the lengths of the squares of the legs, the sum of the squares of the lengths of the legs equals the square of the length of the hypotenuse. And vice versa. If you have a triangle where a squared plus b squared equals c squared, then that had to be a right triangle. All right, so this is cosine, and this is sine. So x squared plus y squared equals 1 turns into cosine squared plus sine squared is 1, no matter what the angle is, as long as it's the same angle both times. That's a trig identity right there, but we're not proving that trig identity, we're constructing it. We just did it. Okay? So, sine squared plus cosine squared is 1. 1 plus 1 is 2. Oh, okay, so 2. And cosine plus cosine is? No, that's multiplying. I'm adding. X plus x would be 2x. So cosine plus cosine would be 2 cosine. There you go. Over sine theta times 1 plus cosine theta. All right, now this is looking a little more hopeful. Do you see it? Do you see where it's going to go? What do you want to do with these 2's? Your favorite F word. Sorry, it's 6 letters this time. Factor out the 2. What's left? Not only. Remember what factoring is. Right, it's dividing. 2 into 2 goes 1. 2 into 2 cosine goes 1 cosine. Over sine theta times, well, guess what? The same thing. Is that a good thing? Is that a good thing to happen there? I keep on wanting to write secant. It's cosecant. Okay. Why? Because what happens now? They cancel and you're left with this. Remember, in your work, never cross things out. Just write what's left. Otherwise, it's really hard to grade what you did. And is that correct now? Is this true? Yeah, because what's cosecant really? 1 over sine. So either I change this to 1 over sine or I change this to cosecant, either way. Yep. Both sides are identical. No matter what you plug in for theta, you're going to get the same thing. So the assumption is if this is an equation, so is that, so is that, so is that. And we go all the way to the very beginning. This is in fact true for all theta. It's an identity. It doesn't matter what theta you plug in. All right, do you see how you work all of that? So in this game, we converted everything to sines and cosines. We could have done that here too. We could have ended up with 1 over sine. That's a good way to go. But everything seemed to simplify nice in terms of sine. So there you go. Okay, is that terrible? Any questions how we did that? Alrighty, let's see. All right, let's try. I think we have time for at least one more. Okay, here we go. So now you know why sine squared plus cosine squared equals 1. Did you ever see that construction before? No? Yes? Okay. All right, here's another one we could try. Tan theta plus cotan theta over secant theta times cosecant theta. And my assertion is that that's always 1. No matter what theta is, as long as this thing is defined, when you plug in theta, you're going to get 1. This is an identity. Am I lying? Can you prove it? Can you disprove it? All right, I'm saying this is an identity. How do you do the identity proof? Any ideas? Can't really add these. They're not like terms. Can't really multiply them, right? So rewrite them somehow. How? How do you rewrite tan? No, not 1 over. Well, you could do 1 over cotan. That's interesting. But I'm thinking it's probably going to be easier if you go to sines and cosines. This is 1 over cotan, so you could do something with that, but then there's no cotan here, so that's not going to help. But if you convert everybody to sines and cosines, you can, right? I think that might help. All right, so this is sine over cosine. What's this? 1 over tan. Well, if tan is sine over cosine, and cotan is the reciprocal, what do you write? Well, or, what is that really? We're saying that the cotan is the reciprocal of tan. What's the reciprocal? Cosine over sine. There you go, perfect. Over. Well, do the same thing here. What's secant? 1 over the cosine. 1 over cosine. Okay. Times. What's cosecant? 1 over the sine. Let's see. Yeah, that's right. 1 over the sine. Yep, that's right. Now, is that equal to 1? I don't know. That's not really obvious yet. You're trying to make it obvious. Okay. Well, let's see. You know how to add fractions, don't you? What would be the common denominator? Sine, cosine, right? So multiply top and bottom by sine. So I got sine squared on top and sine times cosine on the bottom. Plus, multiply top and bottom by what? Cosine. So cosine squared on top and sine times cosine on the bottom. So we got the common denominator. That's good. Let's write down one step at a time. Don't get crazy. Could I write this like this? How do you multiply fractions? Top times top, bottom times bottom, right? Okay. Is this looking good? Do you see where it's going? I think it's looking good. How do you add these fractions now that you have common denominators? Yep, I lost my pen. There it is, okay. Yeah, just add the numerators, keep the denominators. Okay, so sine squared theta plus cosine squared theta. By the way, does that look familiar? You recognize this, yes? That's 1, isn't it? Over sine, over the common denominator, sine theta, cosine theta, over 1 over cosine theta, sine theta. Right, I'm just copying this piece. I added these two guys, there it is. I'm copying this piece, nothing mysterious going on. But what's good about that is this, we already know is 1. All right, and let me just write that. So again, 1 over sine theta, cosine theta on the top. Oops, let's see what we're doing. Right, over 1 over cosine theta, sine theta on the bottom. And the question is that 1? Reciprocal, right. How do you divide one fraction by another fraction? You multiply with the reciprocal. So here's the numerator. And we're multiplying by the reciprocal of the denominator. God bless. And what happens to the cosines? What happens to the sines? So what do you get on this side? What do you have on that side? So check. So that's an identity proof. That's what it is. Yay! Alrighty. Alright, we got a smidgen more time. Okay, let's do one more and then we're good. And that's what your homework is all about, right? Remember the homework is page 450, multiples is 10. Alright, that's the kind of stuff we're going to be doing. Alrighty, try another one like that. How about this? 1 minus sine theta over cosine. Is that the same as cosine theta over 1 plus the sine? Now here we can't rewrite anything because it's already in sines and cosines, right? And there's no fractions to subtract or fractions to add or anything to cancel. This doesn't cancel, even if it said sine here, right? Because that's subtracting. 1 plus 1 what? Oh, if you cross multiply?
No, like the identity is like almost like
1 plus sine squared maybe, or 1 minus sine squared. Yeah, because remember, didn't we just say sine squared plus cosine squared is 1? So isn't cosine squared 1 minus sine squared? That comes in handy sometimes. But I don't have any squares, see? That's not going to help. I don't have sine squared, I don't have cosine squared, so this doesn't apply. Or maybe we could make it so. I'll give you a hint. Remember rationalizing radicals? Right? When we don't like a radical in the denominator, we multiply top and bottom by it to get rid of it. Remember simplifying complex numbers? How do you divide by a complex number? Do you remember that stuff? Do you remember the word conjugate? What if I multiply top and bottom of one of these fractions by the conjugate of this or this? What's the conjugate of this? I think that might help. What's the... No, it's 1 plus already. What's the conjugate? 1 minus, right, okay. All right. Which is actually pretty easy to multiply because don't you get dots? Remember dots? Okay. Or you could do FOIL, but If you follow this out, it's going to be a dots, and you can distribute this. So my aim here is I'm not going to touch this. I'm going to play with this until it looks like that. All right? That's the same thing. That's still an identity proof. All right, so if I distribute the cosine, what do I get? Cosine times 1 minus cosine times sine. Okay. Over. Now this is dots, right? Because first times first is 1. Outer times outer is negative sine. Inner times inner is positive sine, so that cancels. And last times last is negative sine squared. Ah, well there's the sine squared you were talking about before. Didn't we say that sine squared plus cosine squared is 1? And cosine squared is then, if you subtract sine squared from both sides, 1 minus sine squared? So 1 minus sine squared is cosine squared. Oh, that's convenient. 1 minus sine squared is cosine squared. All right, that's right. Let's use that. Instead of that denominator, I'm going to write cosine squared. Now it's good, because look what happens. Well, you want it to look like this, right? Let me copy it over here. Isn't that good? What we shouldn't have done, and it was not obvious to begin with, I shouldn't have distributed it. What if I didn't distribute it? What if I left this the way it was? As it turns out, I didn't need to do it, because look what happens. What's cosine over cosine squared? I just rewrote this way, so undistributed. Factored out the cosine. What's cosine over cosine squared? Cosine on the bottom, right? So the numerator here is that. The denominator here is that. This cosine cancels, right? This numerator here is that. And the denominator here is that. Well, did we do it? Yeah. We did it. Ta-da! You're done. Amazing. Phenomenal cosmic powers. Itty-bitty living space. Alrighty. That's it for today. Have a nice day. See you, YouTube. Nice to